Okay, so we're going to look at a slight variation of Green's theorem, and we're going to compute the outer flux of the vector field xy through the unit circle. So first of all, let's try to see what this variation of Green's theorem is. So the traditional Green's theorem that we have already seen says that if we have a vector line integral over the boundary of a domain, and here we suppose that we have a closed simple curve that defines the domain, then that's equal to the double integral of the quantity q sub x minus p sub y dA over the interior of the domain. And we said that this is usually known as the circulation of the vector field P comma Q. Now, the interesting thing is that to a vector field, we can assign different quantities that are expressed through vector line integrals. And one of them, which is slightly different, is the outer flux. So the outer flux of PQ through the boundary of D is the following vector line integral. Again, D is supposed to be oriented in the counterclockwise way here, and it's P dy minus Q dx. So in other words, to a vector field, we assign this different vector line integral that expresses what part of or what amount of the vector field exits the domain through the boundary. And what really entails is taking a dot product with the outward normal of the boundary of the domain. So in other words, in the circulation, one takes a dot product with the tangent to the domain, in particular when that is facing counterclockwise. So I'm sorry, this should face the other way. And in the case of the flux, one takes the dot product with the outer normal, and that really expresses the amount of the vector field that exits. Now, the interesting thing is that the flux form of Green's theorem, as we say, becomes or is the following. So this is equal to P sub x plus Q sub y. So that's what we integrate over D. And this also has a name. It's called the divergence of PQ. And we're going to see a three-dimensional analog of this. But the bottom line is that people look at this form and they say, okay, this is a new theorem or this is a different formula. But it's not really a different formula. Meaning, if we actually start with this integral and we apply the traditional Green's theorem that tells us what? That we should take whatever is sitting in front of dy and differentiate it with respect to y, with respect to x, and subtract from it whatever is sitting in front of dx and differentiate that with respect to y, then we get exactly p sub x plus q sub y. So it's precisely the same thing. So one now might argue, okay, so for practical purposes, what do we need to do? And the answer is the following. The only thing you really need to know is the definition of the flux integral. Once you have the flux integral, then you can just compute it using the usual Green's formula. And that's the way that I'm going to demonstrate for the particular example that we have at hand here. So let me do the solution. So the vector field is xy, and so its flux its outer flux, to be very precise, its outer flux through the unit circle is given by so what I need to do is take the first component and multiply that by dy, and then subtract from it the second component multiplied by dx. So this is the flux, the outer flux, and this is oriented in the counterclockwise way. So I have this vector line integral. I don't even need to know anything about the flux form or Green's theorem or anything like that. I'm now going to compute this using the one and only Green's theorem that I have, which tells me what? That now my P is this, my Q is this, and I have to compute Q sub x minus P sub y, which is 1 minus -1, which is equal simply to 2. So I have to compute the double integral of 2 over the unit disk. And of course, since I have a constant to integrate, the result will be simply the constant times the area of the unit disk. And what is the area of the unit disk? Pi. So the whole thing is 2 pi. And that's it. So, of course, you can apply you could have said right from the beginning, oh, you know what, if I remember the flux form of Green's theorem, then what I need to take is the divergence of this vector field, which is x comma y. And its divergence will be equal to 2, and you would arrive at the same result. So it's really up to you, but here at least we made the point that it's not two different formulas, it's two interpretations of the same formula. And that's all. Thanks for watching.